Okay, so now let's talk about the algorithm for Newton's method for systems. Okay, so I need a few inputs. Um, so I need to know this system of, or this vector value that's like nonlinear equation. I need to know the corresponding Jacobian. Actually, let's call that x. I need to know the size of the system. I need to know the initial guess. I need to know the tolerance, and I need to know the maximum number of iterations. And then the output is the approximation of the solution and the number of iterations which I used. So I start with the iteration count to be 0, and this stopping flag to be 0. And then as before, while the number of iterations is less than the maximum number of iterations and the flag has not been set, the termination flag hasn't been set, then I perform the iteration, and it's equal to n plus 1. And I have to solve some linear system involving the Jacobian. Sorry. All right, so this is a m by m linear system. All right, so you can solve this. It's like in a variety of ways. It's like you could, for example, use the built-in MATLAB routine, the backslash option. You could use one of your direct solve methods, like LU decomposition with forward and backward substitution. You could use an iterative method like Jacobi or Gauss-Seidel. Since, as I said, this is part of a outer iteration, it probably makes the most sense to try to solve this with an iterative scheme, especially if the system of equations is large. Okay. All right. So once you've solved y, then yn is equal to, alpha n is equal to alpha n minus 1 plus y. And then I can check whether to terminate. So if the norm of y is less than the tolerance, and the residual error is less than the tolerance. Then I set the flag to 1. All right. So, all right. So this is some sort of stopping criterion. And if I achieve the stopping criterion, then I'll stop the while loop. Okay. All right. So that's all there really is to it. And again, it's like I swept some of the details under the rug because you have this linear system which you have to solve, which you would then have to evoke one of the other methods which we discussed before. Okay, so, but it's not so difficult. One of the questions, for example, was how do you go about computing this Jacobian? You can obviously compute that analytically, it's like by hand, or you could use this complex derivative trick, it's like which we mentioned earlier on. All right, and essentially what happens is that in order to compute the Jacobian, you have to evaluate this complex, the complexification, it's like of f m times, right, with a shift, it's like which is a unit vector in each of the m directions, and then sort of assemble it together to get the Jacobian. All right. So anyhow, so that's the basic procedure, and then the next thing we'll discuss are some of the applications. It's like of some sort of for the solution of nonlinear equations, what you can apply it to, And then finally, we'll review it's like some of the methods we've learned and studied it's like thus far for solving algebraic equations, systems of algebraic equations, and so on. So let me just stop here for now.